In the last section, we were talking about discrete random variables, and remember the notion of discrete refers to the idea of finite. And in this section, we're going to talk about continuous random variables and how that kind of manifests itself in a function notation and so forth. The random variable now can be discrete or continuous. When we have a continuous random variable, we have an opportunity for a probability density function. Now, this is related to the notion of a probability distribution. If you've had statistics, then you've heard that kind of phrase. But a probability density function has a graph with these characteristics. The function is positive or zero throughout the domain over which it is defined, and the area under the curve is exactly 1. Now, that idea that the area under the curve is exactly 1 allows us to define this or describe it in terms of the integral notation. And by the way, the function is continuous as well. Now, notice that here's a characteristic then of the probability density function, that the integral from a to b of this function is equal to 1. The area within that interval under the curve is equal to 1. That's the important idea. Now, as kind of an extra idea involved with this, that this area under the curve is going to correspond with probability, and so we can actually find the probability associated with a certain event, and that event is characterized by a value of x falling within a prescribed interval. The probability that x falls between c and d. Let's put a c and d in here. Maybe here and here for c and d. You see, the probability associated with that is all about the area within this region. And that area is the integral from c to d of that function, you see. So we'll get to that in just a little bit. Let's talk about probability density functions and showing that we have that kind of condition. Show that f of x equals that function is a probability density function over the interval from 0 to 1. Well, the first thing we have to establish is continuity and the fact that the function is non-negative. And so f is continuous and non-negative on the interval. We just have to say that. Now, you can see it by putting in values of x from 0 to 1. You can see that the function values are non-negative. And the graph will show you that it's continuous, and we know what that's all about. So, and a way to describe that is that f of x is equal to this. Our function is greater than or equal to 0 over the interval over which we're describing it. Okay, now we want to show that the area under the curve is equal to 1, and that's done by finding the integral. So the integral from 0 to 1 of our function is what we're evaluating. And now I'll kick the 12 out here, and I'll expand, squaring the binomial, and x is multiplied through here, and then I find the integral. The integral function is this x to the 4th over 4, and so on. Now I'm evaluating from 0 to 1. The 0 part kind of is trivial, because when 0 replaces these x's, everything goes out. So we're just finding the value as x is 1. Replacing all these x values with 1, we have a bunch of fractions, and here they are up here. It's 12 times 1/4 minus 2/3 plus 1/2, and collecting using common denominators, we find the collection to be 1/12. Well, 12 times 1/12 is 1. So we have shown here that we have a probability density function. Let's go through it again with a different kind of function. Here's our function, and we're talking about the interval from 0 to infinity. Now, that's kind of an interesting interval over which to show this, but we need to show or say that f is continuous and non-negative on that interval. Now, to find the integral from 0 to infinity, remember that when infinity is involved here as one of our limits, that we have an improper integral, and so we have to set up a limit idea. So it's the limit as b approaches infinity of the integral from 0 to b, you see, of our function. And then we kind of follow our nose from there. The integral is this, and it's rather interesting, the replacements for the b and the 0 when we get to that. When b replaces t, we have this. Okay, that's kind of self-explanatory. When 0 replaces t, When 0 replaces the t, we have a 0 exponent here. E to the 0 power is 1, so this is -1. So this is minus -1, which is going to become plus 1 right here. And the limit as b approaches infinity, as b gets really big, then this negative number becomes large, and the negative idea throws this base exponent situation into a denominator. So we have a denominator that's becoming infinitely large. And when the denominator gets really, really big, the fraction itself becomes small, it approaches 0. So this goes out, and so 1 then is the result of all of this calculation. Now, more normal use or a more typical kind of discussion involving probability density functions has to do with the calculation of probability and the probability that a value will fall within a certain interval. Here with our function, now this is the same function we looked at a little bit ago, but we want to find the probability that x lies in the interval from 1/2 to 3/4. You see, and it's nothing more than calculating that probability by using the integral idea. So it's the probability that x lies between 1/2 and 3/4, and we interpret that as the integral or the area associated with this idea, with the integral from 1/2 to 3/4 of our function dx. Now, I think it's really important to understand what that means graphically, that if we're finding a probability associated with x falling within an interval, then here's what we're really finding. We're finding an area that is associated with that probability. So it is the area within this interval and between the x-axis and the curve. And that area corresponds with the probability that we're talking about. That's the great use of a probability density function. So at any rate, we go through this process, and we've been through it enough times before that I'm not going to belabor this, but we find the value to be 0.262. So the probability that x falls within that interval is 0.262, or 26.2%. Here's a technique that's used rather extensively in statistics. Notice that we have a distribution here, and the area under the curve in this region is 0.3. And that just means that we're supposing that the probability that x falls between 0 and 2, notice in this interval, is 0.3. Now, we want to find the probability that x falls in the region from 2 to 5, that is, x falls into this region. Well, rather than make a big elaborate calculation, we can make a very simple calculation to find that area, because we know that the total area under the curve is 1. And if all of the area under the curve is 1, then to find this area, knowing that, we just take 1 and subtract this. So 1 minus 0.3 would be this probability, this area under the curve. So it's simply 0.7. Interesting technique. We'll bump into it in a minute. Consider this problem. It says the useful lifetime in years of a product is modeled by this equation for t between 0 and infinity. Now, this function we had a little bit ago, and we showed that it is a probability density function. We want to find the probability that a randomly selected unit will have a lifetime of A, no more than 2 years. No more than 2 years. By the way, this lifetime function situation, it might apply to a product like an automobile or a toaster or an air conditioner or something like that. But at any rate, let's look at it graphically and see what we're figuring out. Here's the graph of the function, and we're figuring the probability that this unit chosen at random is going to last between 0 and 2 years. And that simply means we're finding the area under the curve that is in this region. You see, that's all we're doing. And to do that, we use integration. So it's the probability that the time is between 0 and 2 is the integral from 0 to 2 of our function. And we go through the process of calculation. And notice that in this part of it, this is the part where 0 replaces t. And when 0 replaces t, this exponent becomes 0. This e to the 0 power becomes 1, so -1, so it's minus -1. That's where that came from. At any rate, punching the calculator, we find that probability to be 0.181, or 18.1%, if we want to write it as a percent. Now let's make another calculation. Suppose we want to calculate the probability that a randomly selected item will last between 2 and 4 years. Well, again, it's the idea that we're finding a probability associated with an area, and that area this time is between 2 and 4. So it is this area that we're talking about. So the probability that t falls between 2 and 4 is the integral from 2 to 4 of our function. And then going through the process, we find the value to be 0.148. All right, let's answer a third question. The third question has to do with, and I'm not going to move over there just yet, but it has to do with the idea that a randomly selected unit will last more than 4 years. You see, so 4 years to infinity, more than 4 years. So we want all of this area. Now, to make the calculation of all of this area, we can find the integral from 4 to infinity. We can go through that process. Or we can use the technique we talked about before, and I think I'd prefer that. We have the probability associated with this region and this region. We could just add those together and subtract from 1. That is, if we want to find the probability associated with more than 4 years, we can find the probability, you see, of that t falls between 4 and infinity by taking 1 minus the probability that t is less than or equal to 4. Now, t is less than or equal to 4. Gee, there were 2 probabilities associated with this entire interval from 0 to 4. It was the probability that t is between 0 and 2, along with the probability that t is between 2 and 4. And those probabilities were these. Adding them together, subtracting from 1, we find the probability that a randomly selected unit will last more than 4 years to be 0.671, or a little over 67%.